Assalamualaikum and good day everyone. How are you doing? I hope everything is going well with you and your family. Today we will discuss about the logical database design part 1. Okay, let's look at the learning objective of this topic. At the end of this topic, you should be able to first derive a logical data model from conceptual ERD. Second, derive a set of relations from a local logical data model. Third, validate a logical data model to ensure it supports required user transactions. And lastly is merge local logical data models based on specific views into a global logical data model of the enterprise. Okay, in the previous topic, we have learned about the step 1 of the methodology for conceptual database design. So, in this topic, we will discuss on step 2 of the methodology, which translates or transforms the conceptual ER model or conceptual ERD produced in step 1 into a logical ER model or logical ERD. This slide describes the steps of the logical database design methodology for the relational model. In order to build and validate local logical ERD, we need the input such as conceptual ERD and data dictionary. And the outputs that will produce are relational database schemas or relations and logical ERD. Okay, there are a few steps of the logical database design phase. First step is derive relations for local logical data model or logical ERD. So we begin by deriving a set of relations or relational schemas from the conceptual ERD. Second step is validate relations using normalization. Third is validate relations again user transaction. Fourth, define integrity constraint. And next, review local logical data model with user. Then we merge logical data models into global model. This is optional. And lastly is check for future growth. Okay, this slide shows the local conceptual ERD for the staff view of the dream home case study. So we will use this conceptual ERD to demonstrate how to translate this conceptual ERD into a local logical ERD or data model for staff view. Okay, we move on to the first step or first activity of logical database design phase, which is derive relations for local logical ERD. The purpose of this activity is to create relations for the local logical ERD that represent the entities, relationships, and attributes identified in the conceptual ERD. Okay, as you can see here, there are 9 structures that we must consider in a conceptual ERD when we want to derive relations. Number 1 is strong entity type. Number 2 is weak entity type. Number 3 is one-to-many binary relationship types. Number 4 is one-to-one binary relationship types. Number 5 is superclass-subclass relationship types. Number 6 is many-to-many binary relationship types. Number 7 is recursive relationship types. Number 8 is complex relationship types. And number 9 is multi-value attributes. Okay, in order to derive relations for local logical data model, firstly, we examine the strong entity types. Based on the portion of ERD shown in this slide, we can identify entity with primary key as strong entity. For each strong entity in the data model or local conceptual ERD, create a relation that includes all the simple attributes of that entity. for composite attributes such as name include only the constituent simple attribute first name and last name in the relation. For example, the composition of the staff relation shown in this slide is staff consists of staff number, first name, last name, position, sets, and DOB, whereas primary key is staff number. And for the client relation is client consists of client number, first name, last name, and telephone number, and primary key is client number. Okay, next is about weak entity types. For each weak entity in the local conceptual ERD, create a relation that includes all the simple attributes of that entity. The primary key of a weak entity is partially or fully derived from each owner entity. So, the identification of the primary key of a weak entity cannot be made until after all the relationships with the owner entities have been mapped. For example, for weak entity preference in this slide initially map to the following relation. Preference consists of pref type and match rank, and primary key is none at present. So in this situation, the primary key of the preference relation cannot be made until after the relationship has been appropriately mapped. Okay, the next following structure is one-to-many binary relationship types. For each one-to-many relationship, we need to identify parent and child entity by using cardinality. For your information, the entity on the one side of the relationship is designated as parent entity, and the entity on the many side is designated as child entity. So, to represent this relationship, we post a copy of the primary key attribute of parent entity into the relation representing child entity to act as a foreign key. Okay. For example, the staff register client relationship here is a one-to-many relationship as a single member of staff can register many clients. So in this example, staff is on the one side and represents the parent entity, and client is on the many side and represent child entity. So the relationship between these entities is established by placing a copy of primary key of the staff or parent entity, which is a staff number, into the child or client relation. The composition of the staff and client relations is, okay, if you can see here, staff relation here consists of staff number, first name, last name, position, sets, and DOB, and primary key is staff number. And client relation consists of client number, first name, last name, telephone number, and staff number. And primary key of client relation is client number, while staff number here is foreign key. Okay, next is one-to-one binary relationship types. For your information, creating relations to represent a one-to-one relationship is likely more complex. It is due to the cardinality cannot be used to identify parent and child entities in a relationship. So, for this structure, we use participation constraints to decide whether to combine entities to produce one relation or to create two relations and posting a copy of primary key from one relation to another. In order to create relations, so we consider the following participation constraints. First is mandatory participation on both sides of one-to-one relationship. Second is mandatory participation on one side of one-to-one relationship. And the third is optional participation on both sides of one-to-one relationship. Okay, firstly, we discuss on how to create relation to represent the mandatory participation on both sides of one-to-one relationship. In this case, we should combine the entities involved into one relation and choose one of the primary keys of original entities to be the primary key of the new relation, while the other primary key is used as an alternate key. So in this slide, the client states preference is an example of one-to-one relationship with mandatory participation on both sides. Okay, so in this case, we choose to merge the two relations together to produce or derive the following client relation as shown here. Okay, as you can see here, all attributes belong to both entities appear in the merge client relation here. Okay, and please note that relation preference no longer exists and relation client is renamed as client pref. Okay, next is about the mandatory participation on one side and optional on another. In this case, we are able to identify the parent and child entities for the one-to-one relationship using the participation constraints. The entity that has optional participation in this relationship is the parent entity, and the entity that has mandatory participation in this relationship is the child entity. So, we create one relation for each entity, then a copy of primary key of parent entity is placed in the child relation. Okay, based on the example of one-to-one, client states preference relationship in these slides, so we can see that the client entity has optional participation in this relationship. So the client entity would be designated as parent entity and the preference entity as a child entity. So then a copy of primary key of the client which is a parent entity here would be placed in the preference relation as shown here. Next, we talk about the optional participation on both sides of one-to-one relationship. So in this case, the designation of the parent and child entities is arbitrary unless we can find out more about the relationship that can help us make a decision. So, we must try to understand more about the relationship, such as entity which is closer to being optional is the parent, and entity which is closer to being mandatory is the child. Next, we create a relation for each entity, then copy primary key of parent entity into the relation representing child entity to act as foreign key. For example, so consider how to represent a one-to-one staff-users-car relationship in this slide with optional participation on both sides of the relationship. In this case, we assume that the majority of cars, but not all, are used by staff and only some of staff use cars. So based on this situation, the car entity, although optional, is closer to being mandatory than the staff entity. So we can designate the staff entity as parent entity and car entity as child entity. Then we post a copy of primary key of staff entity, which is staff number, into the car relation as shown in this slide. Now we discuss on superclass subclass relationship types. For each superclass subclass relationship in the conceptual ERD, we identify the superclass entity as parent entity and the subclass entity as child entity. Okay, there are various options on how to represent such as relationship as one or more relations. The selection of the most appropriate option depends on a number of factors such as first, disjoint and participation constraints on the superclass-subclass relationship. Second, whether subclasses are involved in distinct relationships. And the third, number of participants in superclass-subclass relationship. Table in this slide shows the guidelines for the representation of a superclass-subclass relationship based on the participation and disjoint constraints. As shown here, there are various ways to represent the superclass-subclass relationship as one or more relations. For example, if the relationship that the superclass has with its subclasses is mandatory and n, so we will produce or create only single relation. And if the relationship that the superclass has with its subclasses is optional and n, so we will create two relations, one relation for superclass and one relation for all subclasses. And for superclass-subclass relationship types that has mandatory and or constraints, we produce many relations depends on number of subclasses where we create one relation for each combined superclass-subclass. And lastly, for superclass-subclass relationship types that has optional and or constraints, we also produce many relations, one relation for superclass and one for each subclass. So you can refer to the figure 17.2 at page 535 in e-book to see the details of various representations of the superclass-subclass relationship based on the participation and disjoint constraint as shown in table 17.1 here. This slide shows the example of superclass-subclass relationship that has mandatory and or constraints. Based on this constraint, each member of the owner superclass must be a member of one of the subclasses, either private owner or business owner, but cannot belong to both. Therefore, we choose guideline number 3 in the previous slide as the best representation of this relationship and create a separate relation to represent each subclass as shown here and include a copy of primary key attribute of the superclass in each relation. Okay, now we discuss on many-to-many binary relationship types. There are two options that we can consider in order to derive relations for this type of relationship. So, for option 1, please consider the many-to-many relationship, client views property foreign, shown in the original figure here. In this example, the views relationship has two attributes called view date and comment. For option 1, firstly, we need to transform this many-to-many relationship by creating two one-to-many relationship and also create one new entity for representing the views relationship. Next, we rename this new entity as viewing, and the two attributes belong to views relationship now become the attribute for viewing entity. And viewing entity now is designated as child entity. And both property foreign and client entities become parent entities in this transform diagram. And don't forget to determine the relationship name and multiplicity for this new one-to-many relationship like shown in the second figure. Then we create relations for this transform diagram. Okay, this slide shows the relations that represent the transform diagram. As shown here, there are three relations that we can produce from the transform diagram in the previous slide, which are property foreign relation, viewing relation, and client brief relation. For your information, the client brief relation actually is the result from our earlier work on deriving relation for one-to-one binding relationship, as shown in slide 10. And as you can see here, for viewing relation, we copy the primary key attributes of parents entities of viewing entity into the viewing relation. For second option, we directly create a new relation to represent the relationship and include any attributes that are part of relationship. Then, we copy the primary key attributes of the entities that participate in relationship into the new relation. So, we consider this attribute now as a foreign key in the new relation. And this foreign key is also the primary key of new relation, possibly in combination with some of the attributes of the relationships. So that's all for the logical ERD part 1, and thank you.